Started recording. Today we're starting on module 8.2. This is a warm-up. Has anyone actually done the warm-up yet? No? Well, I'm going to do it anyway. So, our zeros are -5 and plus or minus 1. That means my zeros or my roots, or my factors, sorry, will be x plus 5 and x minus 1, x plus 1. X minus 1 times x plus 1. That's the factored form of a difference of squares. That means it's going to multiply out to x squared plus 1. All multiply with x plus 5. And when you multiply these two factors together, you get x cubed plus 5x squared minus x minus 5. And there's your answer. Any questions about that? All right, then let's keep going. So, like I said, we're starting 8.2 today. We're going to talk more about polynomial equations. So the first thing we're going to talk about is the fundamental theorem of algebra. And the exact definition is that every polynomial function of degree n is greater than or equal to 1 has at least one zero, where a zero may be a complex number. The corollary to that is that every polynomial function of degree n is greater than or equal to 1 has exactly n zeros, including multiplicity. So what that really means is that the degree of the function will equal how many zeros you have. But those zeros could happen more than once, or those zeros could be complex numbers. All right, so for example, on example 1a, we're asked what is the maximum number of roots of the polynomial? So like the maximum number of individual roots that you can have. The degree of p of x is 5. So since the degree is 5, that means I can have a maximum number of 5 distinct roots, right? You could have less number of roots, but it's that those zeros probably happen more than once. So now what we're going to do is we're going to find all the solutions to p of x and list any multiplicities. So we're going to factor this out by synthetic division. So all the possible zeros will be the factors of -16, which is 1, 2, 4, and 8 and 16. Right? I don't need to worry about the leading coefficient since the leading coefficient is 1. And every factor of the constant over the factors of 1 will just give you the factors of the constant. So I don't need to worry about those. I just need to worry about these. So I'm going to start doing synthetic division with these factors, with these possible zeros. I'll start with 1. And my coefficients are 1, 2, -11, -40, -44, and -16. So drop down to 1. 1 times 1 is 1. We get 3, another 3, -8, -8. And we can see that we're not going to end up getting a remainder of 0. Complete it out all the way. And you end up getting, whatever that is, it's not going to be a remainder. So you can stop. You can tell it's not going to be a remainder of 0. We can stop here. We can cross out the 1 and go on to the next number. So we can go on to -1 and see if that works. The coefficients are 1, 2, -11, -40, -44, and -16. So we'll try this out. Drop down to 1. -1 times 1 is -1. Add going down, you get 1. And you just keep going. And what we end up getting is that we do get a remainder of 0 when you do synthetic division with -1. And then from there, what that tells me is that when I multiply the factor of x minus -1 or x plus 1, that we get from the synthetic division with the quotient that we got from the synthetic division, x to the 4th plus x cubed minus 12x minus 12x squared, sorry, minus 28x minus 16. When you multiply these together, you get your original p of x. But I still need to do synthetic division with this 4th degree polynomial right here because I need to factor it down, and I don't have any other way to factor it but with synthetic division. But the good thing here is that I saw that a factor of 1 doesn't work with p of x. So that means it for sure will not work with this 4th degree polynomial, right? since this fourth degree polynomial is a factor of p of x, if something is not a factor of p of x, it cannot be a factor of any of its other factors. So that means when I'm doing synthetic division with this fourth degree polynomial, I do not need to check 1, because I already know it's not going to work. So I can start right away with negative. Does that make sense why I'm skipping 1, why we don't need to check it? All right, so do synthetic division with negative 1. My coefficients are 1, 1, negative 12, negative 28, and negative 16. Drop down to 1. Negative 1 times 1 is negative 1. I'm going down. 0, negative 12, positive 12, negative 16, positive 16, and we get another 0. So what I have so far is the x plus 1 from the beginning. I have the original x plus 1 that first is synthetic division with. I have this new x plus 1 now. And I have this remainder of x cubed minus 12x minus 16. Everyone with me so far, okay? So we're going to keep going now to synthetic division again. This time with this cubic function right here. So same thing. We try negative 1 again, see if that works again. Coefficients are 1, 0, negative 12, and negative 16. Drop down to 1. Negative 1 times 1 is negative 1. That's negative 1. That's 1. Negative 11, I can see that's not going to work. End up getting negative 5, and that's not too bad. So negative 1 isn't going to work. I can go on to the next number. I can go ahead and try 2. And when I try 2, 1, 0, negative 12, and negative 16, my coefficients. Drop down to 1. 2 times 1 is 2. We get 2, 4, negative 8, negative 16. And again, that's not 0. So negative 1 and 2 both don't work. We'll go on to the next number. We'll try negative 2. So let's go ahead and try negative 2. The same coefficients. Drop down to 1, that's negative 2, that's 4, negative 8, positive 16, and we get 0. So negative 2 does work. So I'm going to pull down the original x plus 1 times x plus 1 that we had, or the x plus 1 squared. I have a x plus 2 now from this negative 2 that I just used. That gives me a factor of x plus 2, and multiply it with my quotient of x squared minus 2x minus 8. And now I'm going to factor out x squared minus 2x minus 8. I don't need to use synthetic division since it's a quadratic, and we can factor quadratic by hand. And we can see that that's going to factor out to x minus 4 and x plus 2. Right? Negative 4 times 2 is negative 8. Negative 4 plus 2 is still negative 2. So when I rewrite this a little nicer, we get x plus 1 squared, x plus 2 squared, and x minus 4. So that's our factored form of p of x, which gives me zeros of x equals negative 1, x equals negative 2 of the x, and x equals positive 4. So I have 3 distinct roots here, but the thing is, some of these roots happen more than once. Like if I look at x plus 1 all squared, that 0 of negative 1 happens twice. So we say it has a multiplicity of 2. So I just put n dot 2 to stand for multiplicity of 2. And then negative 2 comes from x plus 2 squared. It happens twice. So it has a multiplicity of 2 as well. So same thing, we'll just say n dot 2. Right, multiplicity just tells you how many times it's being multiplied. It's being multiplied twice. So there's a multiplicity of 2. And then 4, x equals 4, comes from x minus 4, it's raised to the first power. It happens only once, so it's a multiplicity of 1. You don't have to write anything, it's a multiplicity of 1. Kind of just inferred. So understood to be 1. Any questions about that? Does that make sense? Here's all the work. If you want to take a picture of it or whatever. Take a picture of it. All right, perfect. All right. So now let's go on. Example 2 says write a polynomial of degree 4 whose only roots are 1 and -7. So here, there's going to be 3 different ways to do this. So we have x minus 1 cubed times x plus 7. That is a 4th degree polynomial with only 2 different zeros. Or you could also write x minus 1 squared times x plus 7 squared. That's a polynomial of degree 4 with still the only 2 zeros being 1 and -7. Or you could write it as x minus 1 times x plus 7. All of these have a degree of 4, and they only have 2 roots or 2 different zeros that are 1 and -7. So if I gave you a question like this on a test or quiz, and you listed out any of these 3, it would be right. All 3 of these are possible answers, they're all correct. Any questions about that? Does that make sense? All right. Now let's go on to the irrational root theorem. The irrational root theorem, it says if a polynomial p of x has rational coefficients and a plus b root c is a root of the equation p of x equals 0, where a and b are rational, b does not equal 0, and the root of c is irrational, then a minus b root c is also a root of p of x equals 0. So we've talked about this before with conjugate pairs back in module 4, but essentially what this is saying is that if you have something like a 3 minus, say, 2 root 3, and all the coefficients of your polynomial are rational, or in other words, they're either integers or fractions, then that means that 3 plus 2 root 3 also has to be a root. They always come in pairs. 3 minus 2 root 3, 3 plus 2 root 3. But that only works if the square root of c is irrational, or in other words, it cannot be reduced. If I give you something like 2 plus the square root of 16, 2 minus square root of 16 is not going to be a 0, because the square root of 16 is rational. I can write it as a fraction, right? Because the square root of 16 is just 4. I can rewrite this as 2 plus 4, or just 6. So this does not have a pair, because the square root of 16 is still rational, it's just not reduced to its simplest form. Does that make sense? Any questions about that? All right, and also it only works with square roots. Do not give pairs to cubics. That's not going to work. All right, so now we're going to find the minimum degree of a polynomial with zeros of all these. So when I say the minimum degree, what that means is I want all my zeros to have a multiplicity of 1. Or in other words, I want to cancel out anything that repeats. So the first one I see is 0. So 0 is fine. I don't have to add anything to it. Next, I have 2 minus root 3. That's in the form we just talked about. So that means 2 plus root 3 has to be a 0 as well. Next, I have a 2. That's fine. Nothing to add to it. Then I have -7 plus root 3. That's in the form we just talked about. So we have to add -7 minus root 3 as another 0. And then I have root 3 plus 2. Well, root 3 plus 2 is the exact same thing as 2 plus root 3. I don't want to count it twice, so I'm going to get rid of this 2 plus root 3, or root 3 plus 2. It's the same thing as the 2 plus root 3 that we added. I don't want to add it twice, so I'm going to get rid of it. Next, I have 7 minus root 3. That's still in that irrational form we talked about. So you have 7 plus root 3. We have to add that 7 plus root 3. After that, I have 5 minus the square root of 9. So remember that irrational root theorem only works if the square root is actually irrational. The square root of 9 is not irrational because it's equal to 3, and 3 is a rational number. So I can rewrite 5 minus the square root of 9 as 5 minus 3, or 2. But the problem with that is that this 2 already showed up before, and I don't want to double count any zeros. I want all my zeros to have a multiplicity of 1. So I'm going to go ahead and cross out 5 minus the square root of 9. Does that make sense? Why? Are we okay with that? And then I have negative root 2, which means I have to have a positive root 2 as well. Right? 0 minus root 2 gives you 0 plus root 2. So if you count all these zeros up, we end up with 10 possible zeros. or a minimum degree of 10 zeros. You could have more if you have a multiplicity of more than one, but the absolute minimum number of, or the degree of the polynomial, the absolute minimum degree of that polynomial is going to be 10, because that's how many distinct zeros that we have. Any questions here? Are we okay? All right, let's go on to the last problem. Example 4, write a polynomial function with integer coefficient and minimal degree with zeros of -1 and 3 plus root 2. So if I have a 0 of 3 plus root 2, I have to have a 0 of 3 minus root 2 as well. So that means when I write my factor form out, I have x plus 1, x minus that 0, 3 minus root 2, and x minus the other 0 of 3 plus root 2. So this looks kind of hard to multiply out, right, with all the roots and everything. The good part is there is a trick to multiplying conjugate pairs together, or just those pairs together. The trick is to set x equal to one of those pairs, either 3 plus root 2 or 3 minus root 2. It doesn't matter which one. So let's say x equals 3 plus root 2. And then you subtract the 3 over, you get x minus 3 equals root 2. Or in other words, you want to isolate the radical. So isolate the radical, you get x minus 3 equals the square root of 2. And then you want to square both sides. X minus 3 squared gives you x squared minus 6x plus 9. And that's an equal 2. Subtract the 2 over, you get x squared minus 6x plus 7. Or in other words, x minus 3 minus root 2 times x minus 3 plus root 2 multiplied together to x squared minus 6x plus 7. Everyone okay with that? You remember that back from my module 4? We good? Okay. And then we can multiply the x squared minus 6x plus 7 with x plus 1. So let's go ahead and multiply with x plus 1. And when you do, you get x cubed minus 6x squared plus 7x plus x squared minus 6x plus 7. Add my terms, x cubed minus 5x squared plus x plus 7. And that's your final answer. Any questions about that? So this is very similar to what we did yesterday. The only trick here is that with conjugate pairs, there's a very easy way to multiply them together. Instead of trying to distribute all that stuff together, you just set x equal to one of the two of the pairs, isolate the radical, and then square both sides. And you'll see we'll do the same thing tomorrow when we deal with complex numbers and complex conjugates. Any questions? Are we good? Comments, concerns, complaints? Great. That's the homework. And I'm going to turn off the video now.